Yeah, hello, welcome back. Like I said in this video, we're going to look at the distribution of Zn. Okay, so many of the key properties of a branching process just revolve around the distribution of this Zn. So kindly pay attention to this video very well. Okay, so the PGF, we've not gotten there yet, but it's very important when we are studying the distribution of Zn. Okay, so we say that consider the population size at time n minus 1. So we say the generational size random variable is given by Zn minus 1. Okay, and we are to label the individuals. So the individual labels at this generation Zn minus 1 are 1, 2, 3, all the way to individual Zn minus 1. Don't forget. Okay, and each individual starts a new branching process. Let's not forget about that. And the family sizes are respectively y1, y2, all the way to yzn minus 1. So if these are all random family sizes of the individuals, then we say that the number of individuals at time n, that's Zn, is equal to the total number of offsprings of the individuals 1, 2, to Zn minus 1. So that is, to get the generational size at time n, we need to sum the family sizes from the first individual to the individual Zn minus 1. We are saying this because to know the number of people that are alive by generation n, we need to reference it to the previous generation, that is generation n minus 1, and the last count or last label count of the number of offspring in the previous generation, that is generation n minus 1, it is the individual Zn minus 1. It looks like a generation though, but it's like a label count, so that we don't get confused if we want to know the last person, because the family size in the generation n minus 1 is random, so we don't know. So we just use the last person to denote that generation that we actually reference to. So this is from generation n minus 1, so that person is going to be individual or offspring number Zn minus 1, and the family size is going to be yzn minus 1. You get it? Meaning, to get Z3, it should be equal to y1 plus y2 plus yz2. Okay, to get z5 should be equal to y1 plus y2 plus y3 plus yz4, right? Good. So this is seen as a randomly stopped sum of what? The family sizes in the previous generation, right? Good. Each of these family sizes, yi's, are iid because they approximately become the same as y, because we have the same identical family size distribution, right? Good. So let's look at the PGF of this Zn. The PGF is seen as the probability generating function of the family size random variable, and we want to look at it with respect to that of Zn for each generation, right? But first of all, let's look at the PGF for that of the family size. Before we do that, let me tell you what PGF does. We all know what moment generating functions are. They help us generate moments, okay, by a random variable. Now, for a probability generating function, like the name suggests, it helps us to put all the probabilities into one word formula or one function, okay, and that's the PGF. Moment generation functions can be used for both discrete and continuous distributions, but for that of a discrete distribution or the PGF, it can only work for discrete positive integer value random variables. So now, this family size random variable we all know is positive what? Integer valued. So that is why we can use PGS for it. If even a particular distribution, discrete distribution, does not take positive integers, we cannot find the PGF of it. PGF related functions should only have positive integers, right? Non-negative integers, right? Sure. So to find we put all these probabilities into one function, and when we want to recall this one, we say that the PGF is a probability that is a dummy variable function in S, where S is a dummy variable. So to find the probability that maybe y is equal to 0, y is equal to 1, and so forth, if you want to find the probability that y is equal to 1, of course you just take the first derivative of the PGF and equate S to be equal to 1, and you find the probability that y is equal to 1. That's how we do it. If you want to find the probability that y is equal to 2, all that you do from the PGF, you can use the PGF to do that, to recall the probabilities that were in the family size random variable. All that you do is to find the second derivative and equate S to be equal to 2, and you get your probability. It's as simple as that, right? Good. So this PGF is seen as the expected value of what? S to the power y, that dummy variable, to the power the family size random variable, where this y could either be 0, 1, 2, 3, and so forth. And remember, before we find the expected value, we need to multiply it by what? This random value by the probabilities, right? Good. So let's move forward. We know this, that the Zn is equal to the sum of the family size random variables for the previous generation, right? Good. So PGF at time n, that's g subscript Zn of S, should be equal to, it's like a function of another function, a Goff function, right? Maybe if I have a function g, have another function f, so g of f, that's a Goff function, a function of another function. So we say that the family size random variable y, the PGF is gy of s, which is the same as z1. So if you add z1 and zn minus 1, you are going to get zn, right? So to find the PGF at generation n, we can say that this is the same as the PGF at generation n minus 1 of the PGF of the family size random variable. You get the same thing, right? Good. So let's pick an example. A lot of talking, let's show working, right? So the PGF of a particular family size random variable is given by this function. Now, can we recall the true nature of the probability mass function of this family size random variable? Yes, we can do that. Remember, we said this PGF is the same as expected value of S to the power y. So let's see. If we pick S to the power 0, what do we get? We get 1, right? So 1 times the probability. We've not brought the probabilities in. Remember, to get the PGF, we need to multiply by the probabilities. Meaning, our probability is going to be 0.2 for probability that y is equal to 0. And S to the power 1, meaning y is equal to 1, meaning the probability that y is equal to 1 is 0.5, and that of y is equal to 2 will be 0.3. Okay? So that is that for the PMF being extracted from the PGF. Let's look at the PGF for generation 1. So to do this, we know that it's simply the same as what we were given. Okay? Let's look at that of generation 2. So generation 2 should be a function of what? Of the other function. That's the first PGF. That's g of s. So now, this is what we mean. So g of s, which is the same as this function. So this function now is like the random variable at hand. Okay? We'll finding the PGF of it. And to find the PGF, we need to multiply the random variable by its probability. So the first probability is what? 0.2. So 0.2 times the random variable. So now our y has now become everything here, because that's our dummy variable now. So 0.2 times everything here to the power 0, that will give us 1 still. So I left with 0.2. So we pick the next one, 0.5. That's the next probability times the same random variable to the power 1, because 0.5 is the probability that y is equal to 1. So to the power 1 will give us this. And the last one with probability 0.3, so to the power 2. Okay, that's okay. So this is a function. You realize that it's becoming more complicated than we think, right? Let's look at the PGF at generation 3. So it will be seen as a PGF, okay, a function of another function at generation 2. So generation 2's PGF of the family size random variable, because this is 1. So 1 plus 2, you get 3. So this is okay. So I'm going to pick the previous PGF, okay, and we do the needful just in that order, right? You can see that this is even more complex than we think. Very, very complex, right? Good. So it should be a function of the previous PGF that we had. And you see this whole thing becomes a random variable on its own, and that will be more complex. So you can see that it's not easy to simplify by hand, but the concept is that you are building the PGF of generation and repeatedly by composing the family size PGF, right? Great. So we all know that for simplicity purposes, we are going to look at the PGF at generation n just to make it Zn of s, and out of this to be Zn minus 1, G of E subscript n minus 1 of s, and so on, right? Yeah. And for the purposes of simplicity again, instead of making G y of s or G1 of s, we are going to just make G of s as our random PGF. Okay. Yeah. So this looks like a recursion formula. Okay, so if you want to find the PGF at generation n, all you need is the PGF at generation n minus 1 of the PGF of the first generation. Okay, so we know the PGF is the same as expected value of what s to the power Zn, that's for generation n, and so forth for the other ones. So this is okay. Yeah, so this is like a recursion, as I said, equation 1. I've introduced it in the previous slide already. Yeah, so this is like a recursion. So a recursion, just continuation, that's fine. So if you want to find the PGF at the m generation, we can reference to that of the third generation, but you need to do the GOF function, the function of another function for that of the family size PGF 3 times, meaning to find for, you can also do it for n times like you see here. So this is just like a general recursion formula. All right, good. So we all know this is what I've just given. We know that the PGF is given by summing all possible values of the random variable y, the probability times s to the power y, and that's the PGF for the family size distribution. Okay, yeah. So we call that one this is the n-fold iterate of what the G. So we are going the family size distribution. We're finding a function of itself for n times. So that's the n-fold iterate of what the family size random variable to give us the m generational PGF, right? Good. So we've been talking plenty, but we've not picked a particular family size. We've not assumed that maybe y follows some particular family size distribution that we find the PGF of it, right? So let's consider that it follows the Poisson distribution. So how do we find the PGF of the family size random variable? We all know that the PGF is expected value of s to the power y. So we're going to say that, okay, so if our y is equal to k, probability that y is equal to k is given by a Poisson random variable. We all know that the PMF is given by this, e to the power negative lambda to the power k divided by k factorial. Then, because this is a probability, but we are multiplying by the random variable for the PGF, which is s to the power y, but our y is k. So that is it. We can simplify remember, multiply numbers with the same base, we can actually bring them together, indices. So that is why we have something here like that. E to the power negative lambda is here still, right? So e to the power negative lambda is like a constant because we are summing for k. So k cannot be found here. So e to the power negative lambda is seen as a constant. So we can bring it out, and now our expression becomes lambda s to the power k divided by k factorial. And from our Taylor series expansion, if you look at this clearly, this will give us e to the power lambda s. So check that one very well. You give us e to the power lambda s, and by simplifying these two, this is indices as well, we get e to the power negative lambda s minus 1. Okay, s minus 1, and that gives us this. You can see family size PGF. It's like what we got it up here. So by generation 3, if you do this recursively, you are going to get this fearsome expression. All right, good. That's okay. So we end here, and thank you so much for being with me. God bless you.